This video will be about acid-base reactions and equilibrium. Acids can be defined in three ways: Arrhenius acids, which are H+ donors in aqueous solutions; Bronsted-Lowry acids, which are H+ donors; and Lewis acids, which are electron pair acceptors. Acids, under Arrhenius and Bronsted-Lowry definitions, have an H bonded to a polyatomic ion or other elements. Bases can be defined in three ways as well. Arrhenius bases are OH- donors in aqueous solutions. Bronsted-Lowry bases are H+ acceptors, and Lewis bases are electron pair donors. Bases usually have an OH- group or have a nitrogen bonded to some hydrogens, such as NH3. pH is the negative log of the H+ concentration. This ranges from 0 to 14. pOH is merely the negative log of the OH- concentration. You'll see more of this later. Just know that pH and pOH added together make 14. So if you know the pOH, you can figure out the pH and vice versa. What about weak and strong acids and bases? Weak acid doesn't dissociate in water because it is at equilibrium. An example of this is acetic acid, HC2H3O2. The first reaction shows the equilibrium of acetic acid, while the second equation shows the equilibrium of acetic acid in water. In both cases, acetic acid does not fully dissociate. A strong acid dissociates completely in water, or in an aqueous solution. Most acids where hydrogen is bonded to an atom of very different electronegativity are strong, with the exception of hydrofluoric acid, which is a weak acid. This is due to the small size of the fine ion, which holds hydrogen stronger than other halides. This makes an unstable conjugate base, which I'll explain more of later. Basically, it's due to intermolecular bonds. The strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and sulfuric acid, but only the first H. Strong bases are any group 1 or 2 alkali or alkaline earth metals bonded to an OH- group. These will completely dissociate. Anything else is a weak base and will not dissociate. So what does a conjugate acid or base mean? A conjugate acid or base is the part of the acid or base without the H+ or OH-. An acid has a conjugate base, while a base has a conjugate acid. The stability of this conjugate acid or base determines the strength of the base or acid, respectively. But more often you hear the salt of an acid or base. A salt is the anion and cation released when an acid and base are combined to form water. The general formula for this reaction is HX plus MOH goes to H2O plus MX, where HX is the acid, MOH is the base, and MX is the salt. Acid-base reactions. As shown before, acids and bases often react to form water and salt. The thing with acid-base reactions is that the conjugate acids or bases of strong bases or acids will not have the strength to reform the salt. Essentially, these become spectator ions. This is shown in the reaction between hydrochloric acid and ammonium hydroxide. The first equation doesn't actually form. Instead, you have a second equation because Cl- is a spectator ion. But what about those weird bases like NH3? This breaks down like so. This is a general question. The answer is the explanation of buffers. A buffer solution resists change in pH. A buffer consists of a weak acid or base and its basic or acidic salt. An effective buffer resists change in pH because of Le Chatelier's principle. If something happens to disturb the equilibrium of a buffer, such as the addition of another acid or base, it shifts to maintain equilibrium. In the case of a buffer, when the balance of acid or base and the salt is upset, the ratio does not change much as long as the amount of OH-, H+, or salt added is small. In the case of strong acids or bases, as long as the buffering capacity is not exceeded, strong acid or base is consumed by the reactions with the buffer. pH range of a buffer is the range where it acts efficiently. After this, it will change pH rapidly and level off. See you later for titrations. So basically, this is a spew-out information question that asks for a detailed definition of a buffer. The other questions will build off of this. This is an application of the definition of a buffer. You need to determine which of these makes a buffer and which has a pH close to 9. A pH close to 9 implies a base, so this is a basic buffer. Let's start with Archie A. Archie A says that he would mix acetic acid and sodium acetate solutions. Acetic acid is a weak acid, and the solid NaC2H3O2, essentially C2H3O2- because of the dissociation of Na+, is relatively weak as well. A pH close to 9 implies a weak base, so this buffer solution, because yes, it is a buffer, would be acidic and have a pH far from. Beulah B said she would mix NH4Cl and HCl solutions. HCl is a strong acid and NH4Cl is an acidic salt. As an R2 solution, this would not have a pH close to 9. Additionally, this is not a buffer because it contains a strong, not weak acid and will not resist change in pH. Carla C. said she would mix NH4Cl and NH3 solutions. NH3 is a weak base and NH4Cl is an acidic salt. NH4 plus, because Cl minus dissociates, is the salt of this base. Because NH3 is basic, its pH will fall between 7 and 14. This solution would be a buffer because it's a weak base and it's salt, and due to the NH4, which is a base, it's reasonable enough to say that this would be a buffer of pH about 9. This is the correct procedure. Finally, Dexter D. He said he would mix NH3 and NaOH solutions. NH3 is a weak base, and NaOH is a strong base. These are not the correct components of a buffer and will not be close to a correct procedure. The concepts applied in this question were buffers and strong and weak acids and bases. It was enough in this question to know these concepts, but they gave you a pKa. This is like pH, but instead of the negative log of the H plus concentration, it's the negative log of the Ka. This is where titrations come in. That will be explained in the next question. Before we talk about the next question, we have to talk about titrations a little bit. This is a titration curve. It shows how pH changes with additional NaOH added. A titration is a process in which a strong acid or base of known molarity is added to a buffer, usually to determine the molarity of the weak acid or base. Some things to know about titrations. The first region on the graph is the buffer region, right here. Here, not enough base is added to affect the buffer. The second region is where the changes really happen. Two substances reach equilibrium, equal amounts of each is present, and the pH changes dramatically. The middle of this is called the endpoint, right here. This is where the system is truly at equilibrium and can be used to determine the molarity of the unknown acid or base. The last region is not a buffer region. That's right here. It's merely where there's more base than acid, so the pH remains high. Titration math often deals with several steps if you're working with theoretical data rather than experimental. What we have in that graph is experimental data. If you're given like the amounts added after a certain amount of time and something like that, and then you're going to have to work with math. Use the common ion effect to determine the new amount of acid or base and conjugate acid or base present. Using another icebox, find the new concentration of H plus or OH minus, then determine the pH. Finally, as mentioned before, pKa has to do with the titrations. The pKa equals the pH at the half equivalence point. Just like it sounds, this is halfway to the equivalence point. If you know the pH at the half equivalence point, you know everything.